In this first Proton NMR video, I'm going to look at the simplest type of Proton NMR spectra, and then in a subsequent video I'll take it a step further where we'll look at the extra detail that Proton NMR can give us. So we'll just start off with the basics. Works in exactly the same way as carbon-13 NMR. So you would have your sample, so in this case it would be ethanol. You'd have your sample in a tube with a solvent, and the solvent can be the same as it was in carbon-13 NMR, so that's CdCl3. Remember, deuterium has an even number of nucleons, that's the particles in the nucleus, so they don't possess a property called spin, or their nuclei don't possess that property of spin, and so they won't give a signal in an NMR spectrum. There's also a reference molecule in there as well, and the reference molecule is still TMS, so that's tetramethylsilane. And so what happens is you apply radio waves to the molecule, and it sets about measuring the amount of energy required to flip the nucleus spin state from that in the same direction of the external magnetic field to the opposite spin, and that's the resonance part. So if we think about ethanol, the protons in ethanol, or the hydrogens in ethanol, first of all we need to think, well, how many different environments have we got for our protons? So if you have a think about that, pause the video and then I'll continue. So you'll notice the protons have changed colour, so we've got a green environment, a red environment and a blue environment. So the different colour represents the different environment, and what that means is they will absorb slightly different amounts of radio wave frequency to make the spin states flip round, because they experience their own slightly different magnetic fields. So if we look at the environment that these green hydrogens are in, that's a hydrogen bonded to a carbon, just bonded to another carbon with hydrogens on. So that would be classed as this RCH environment. And so we would see a peak somewhere in that region between just before 1 and 2 ppm. So if I just write that there, between 1 and 2 ppm. Then if we look at the red protons, we've got a hydrogen bonded to a carbon, which is singly bonded to an oxygen, and that is this environment here. So that's the HC single bond O environment, and that's somewhere between 3.4, 3.3 and just over 4. So we'll say 3.4 to 4.3 ppm. And then the blue proton is a hydrogen singly bonded to an oxygen, so that's obviously here. We've got a very broad range here, and I'll talk about OH protons in another video. So we've got a very broad range which is between 1 and just below 6, so we'll go 1 to 5.7 ppm. So you can see I've drawn up a very rough spectrum for this molecule. So we've got the green peak here, so that's due to these green protons here. So I've decided on 1.5, so between this range here. The red ones between 3.4 and 4.3, so I've gone for about 4 ppm. And the hydrogen in the blue environment, so the OH hydrogen, anywhere between 1 and 5.7. So I could literally have put a blue peak anywhere between there and there. I've gone for 3. Just a quick reminder of the scale that we use. Remember, if we go back to this test tube, we've got the sample, so the ethanol, the solvent, which we don't want to give a signal, a confusing signal. and the reference peak is TMS, and that gives us the 0. I haven't drawn a peak in there, but sometimes you do see a little peak there, and that's due to TMS, and that gives the machine its reference value for 0, or reference peak for 0, and then everything's measured against that. So it's the difference scale because it's comparing the energy to resonate the different proton environments compared to the protons in TMS. So if you want to test yourself on how many environments you can spot within some organic molecules, you can have a go at these 3. All alcohols. So we've got propan-2-ol, we've got butan-2-ol, and we've got 2-methyl-propan-2-ol. So if you want to have a think, how many proton environments have we got in each molecule, and then I'll go through the answers. So if we look at number 1, we've got hydrogens in this environment here. These 3 are all equivalent to each other. Is there another set of hydrogens that are the same as those? Well, there are. So I'll colour those in green. It's these ones here. So these CH3 groups at the ends of the molecule are actually equivalent to each other, because if you consider what they are bonded to, it's identical. We've got a unique environment here, and we've got obviously a unique environment there. So in propan-2-ol, we've got 3 environments. So if we look at butan-2-ol now, so we'll go for this one first. So there's an environment there. Now we need to ask ourselves, is this CH3 group equivalent to this CH3 group? So think about, well, what's it bonded to? Hydrogen, carbon, then a CH2 group. Whereas these ones, hydrogen, carbon, and then we've got this CHOH group. So they're different, so we need a different colour. So I'll colour those in orange. And then there's only one CH2 group in this molecule, so that will have to have its own colour. There's only one H bonded to an oxygen, so we'll go for blue for that one. And last but not least, we've got this hydrogen here, which is in its own unique environment. So altogether, we've got green, red, blue, purple, orange. So we've got 5 environments. So if we go for the third molecule now, so this is 2-methyl-propan-2-ol. We'll go for this CH3 group first. They're obviously equivalent to each other. We need to ask ourselves, are the hydrogens in this CH3 group equivalent? Well, let's think. This CH3 is bonded to a C with 2 CH3 groups on and an OH. This CH3 group is bonded to a C with 2 CH3 groups on and an OH. They're equivalent. And this one is also bonded to 2 CH3 groups and an OH. So all of these protons are actually equivalent. So obviously the hydrogen on its own bonded to that oxygen is different. And so we've got 2 environments in this one. So we'll just finish with a quick summary there of Proton NMR in its simplest form. What does it tell us? Well, the number of peaks tells us the number of different proton environments, and the shift value, so that's where the peak lies on this scale. Remember, it's the delta scale measured in ppm, measured relative to TMS, tetramethylsilane. The shift value tells us what type of environment the hydrogen is in, and we would always be supplied with this data sheet, and so we can always read off the value and work out what the environment is. So just a quick example, if we see a peak between 6.5 and 8, well, it could be a hydrogen bonded to a benzene, it could be a hydrogen belonging to a phenol, or it could even be, because it continues up here, it could even be this environment here. So this is C double bond O NH2, or C double bond O NH.